Hey everyone, this is Animesh and welcome to the Gate Mantra. So, last video we have seen the working of the MOSFET, the working of the N-channel MOSFET, or we can say P-type MOSFET or N-MOS. Okay. So we have seen the current equation also for the MOSFET. Okay, for the N-MOS. Now, now we are going to see. Okay, the channel length modulation. Okay, what is the channel length modulation? So before starting the channel length modulation, we want to recall our last case, that is the fifth case, okay, where we are increasing the drain to source voltage, then our so here we are increasing our drain to source voltage in the two step. First step, in first step we are increasing the drain to source voltage by a small amount. So in this case, okay, in this case we have seen that our current id, okay, the drain current is also increasing linearly, right? Our drain current is increasing linearly, okay, when we are increasing vds by the small amount, right? And we have also seen that our channel is uniform. Okay, now when we increase, okay, here in the graph between the id and the vds for the small value, now when we increasing our vds, okay, more than 15 millivolt or into the large value, right, then we have seen that the voltage between the gate and the channel is decreasing as we are moving from source to drain, right? So at source in the voltage is vgs and at the drain end the voltage is vgd, okay, gate to drain voltage, right? So this vgd nothing but the vgs minus vds, right? Okay, and we have seen that when we are increasing the vds, drain to source voltage, our channel is no longer uniform, okay, it's become tapered in the shape. And when, okay, it's become tapered in the shape, right? And when the vgd is greater than vg naught, this region is, we call this region of operation in the linear region, okay, or in triode region, where the gate to source voltage, okay, changed the resistance of the channel, right? Now in this region of the operation, okay, the voltage, the velocity of the electron, okay, the velocity of the free electron that are moving into the channel is less than the critical velocity, we can say, okay. So or saturated velocity, we can say, right? So here we assume that, okay, here we are increasing drain to source voltage, right? And our channel become more and more tapered, and when the vgd is less than vt naught or less than threshold voltage, right, the channel pinch off at the drain end. This means the charge, the free electron present here is zero, or we can say that the depth of the channel is zero at the drain when the vgd is less than the vt. And we have also seen that theoretically, if we increase, okay, and this voltage at which, okay, and this voltage at which this happened, okay, the pinch off happened is known as the vd sat, okay. And as we have seen that when we are increasing the vds beyond vd sat, then the shape of the channel is not changing, okay, shape of the channel is not changing. It means its pinch off point is only at the drain it, okay. This is the theoretical concept, practically it's not happened, okay. Now we are going to see what happened when the vds is greater than the vd sat practically, okay. Theoretically we have seen that when the vds is greater than vd sat, okay, the channel shape is not changed, is tapered, is pinned up at the drain end, right? And the current of the, okay, and the current flowing through the channel in this region is become saturated because of the increasing the resistance of the channel. The velocity of the free electron in the channel okay, is getting saturated. That's why the current is getting saturated. Now we are going to see the practically what happened when we increase the drain to source voltage beyond VD side, right? So here we have seen the current equation, right? So here is our MOSFET. Now what we are going to do, we are doing the connection here, right? So here I am connecting. Here let's make connection. We are applying VGD, sorry, VGS greater than VT naught. Make the channel 2, right? Here we are connecting the drain to source, right? So we are making source a negative potential, drain and the positive potential. But we are also doing, we are connecting source, body, bulk or to substrate, and we are keeping this substrate, right? So what is this? This is the VGS. This is greater than VT, and what is this? VDS. This is the VDS. We are increasing the VDS, okay? So we have seen that as we are increasing, okay, there here is the free electron present here. Here is the, you can say the channel is created because the VGS is greater than the VT naught, right? Channel has been created here. Now what happened? As we are increasing, okay, as we are increasing the VDS by the large amount, okay, large amount, the voltage across the channel, okay, as we are moving from source to drain is decreasing. Because of that the depth of the channel is decreasing, okay, and initially the depth of the channel was uniform like this, okay, and as the VDS is increasing, okay, the depth of the channel is decreasing like this, because here the voltage is between gate to drain is VGD, okay, and here VGS, okay, and the VGD is nothing but the VGS minus VDS. So as the VDS increase, the VGD decrease, and when, and due to that the depth of the channel is decreasing here, right, at the drain end. And when the VGS, when the VGS, sorry, not VGS, when the VGD, right, when the VGD is less than VT naught, okay, then pinch off occur, is less than equal to VT, pinch off occur at drain end, of occur at drain end, right? So VGD is VGS minus VDS less than equal to V naught, is less than equal to VT naught. Hence here the VDS greater than equal to VGS minus is the condition for the saturation, right? So we said that, okay, we have also seen that now the MOSFET is goes to the saturation when we are increasing the VDS greater than the VD side. Now this we can say, okay, VGS minus VT naught we called is as a VD, okay. Now we are going to see what happened when the VDS is increasing beyond the VD side, because earlier we have seen that when the VDS is greater than the VD set, then the shape of the channel are not changing. okay, not changing, and the current become constant, and we can say that, and we was saying that, okay, the MOSFET was in the saturation region, right? So what happened when we increasing the VDS beyond the VD set? So when we increasing the VDS beyond VD set, this pinch off point, okay, this pinch off point is start moving from drain to the source end, okay. This pinch off point start moving, right, pinch off point start moving like this from drain into source in, okay, as we are increasing the VDS beyond the VD set. Due to this, okay, due to this, okay, the electron, and one thing also we, okay, we need to remember that the voltage across the channel, okay, and if the pinch off point is moved to this point, okay, then the channel is only this much, okay, and we know that the voltage across the channel is going to be constant, and it will be equal to the VD set, okay, and the rest voltage, okay, that is greater than the VD set is appear across the depletion region, so let me draw once again, so we have seen that thing like this is the source in and this is the drain in, right, and we have seen earlier our channel is like this in form, our channel is like this, okay, and as we are increasing the drain to source voltage, our channel become tapered, okay, our tapered like this, and when the VGD is less than the VT node, channel is pinch off at the drain, and now when we increasing our VDS, okay, greater than the VD set, okay, the voltage we have seen that, okay, the voltage along the channel will be remain same, that will be equal to the VD set, that will be equal to the VGS minus VT naught, right? So as we are increasing the VDS, our pinch off point is moving, okay, toward the sourcing. So if our pinch off point is here, okay, then we know that the voltage across the channel is remain constant, so we can say that, let me remove this, okay, to understand more clearly. So what we have seen that our channel voltage is remain constant, and this will be equal to the V, okay, and the rest of the voltage, okay, it's appear across depletion region, right, the V minus V, okay, and now our effective channel length will be this much, okay? Because our channel is effective channel length is getting reduced as we are increasing the drain to the source voltage. Now our effective channel length will be this much, and this is the depletion region length delta L, okay. So our effective channel length is getting reduced, getting reduced, right? So this is the delta L, and this much was our channel. Now this is effective channel length, okay. So our effective channel length will be L effective will be equal to, this is the total length is L, so L minus delta L. And as we know that in saturation region, okay, in saturation region we write the equation for the drain current is like, okay, id IDS is equal to IDS is equal to 1 minus 2 sorry 1 divided by 2 COX 2 by L, okay, EGS minus, right. So here in because of increasing the VD, yes, because of increasing the VDS, okay, our effective channel length is decreasing, our effective channel length is decreasing. So here when VDS is greater than VD set, we can write here IDS will be equal to 1 by 2 continuum COX, and we will write W by L effective, okay. Earlier our channel length is L, now our channel length is become L effective, okay, and this VGS minus VT not whole square, right. Now I am replacing this L effective by L minus delta of, then 1 by 2 even COX W, okay, L minus delta of L, okay, VGS minus VT not whole square. Now I am taking common this L, okay, so here 1 by 2 UN COX, okay, divided by 1 minus delta of L divided by L, okay, into W by L VGS minus VT not whole square. Now let's see. Now we can write this as 1 by 2 nu n, okay, COX, okay, and 1 minus delta L by L, okay, to power minus 1, and W by L VGS minus VT whole square. Now we can write this as IDS will be equal to 1 by 2 nu n COX, okay, here is express this one, okay, express this one. So here COX here is 1 plus delta L by L, okay, and then W by L GS whole square, right. So here as we know that, okay, as we know that as we are increasing the VDS, okay, our delta L is also increasing, right. As the VDS is increasing, okay, the excess voltage appear across the depletion region, that is the VDS minus VD set, and due to this our depletion length, okay, or depletion region length is increasing. So we can say that due to this VDS is equal to lambda dash, sorry, we can say that from here, okay, when we are increasing the VDS, okay, when we are increasing the VDS, okay, our depletion region length is also increasing. So here we can say that delta L will be equal to the lambda dash and VDS. As the VDS is increasing, delta L is also increasing. As the VDS is changing, the depletion region length is also changing, right. So where L dash is process technology parameter, okay, where L dash is process technology parameter, we can say L dash is process technology parameter dimension. What will be its dimension? Dimension will be micrometer per volt, right. Now see here, so uh, I will just put the value of delta L here. then it will become 1 by 2, okay, nu n c 1 by 2 nu n cox, okay, and this will be 1 plus lambda dash vds divided by L, right? Here W by L VGS. Now let's assume, okay, this lambda dash divided by L will be equal to lambda, and this lambda is process technology parameter. Process technology parameter, and its dimension is volt inverse, okay, and its dimension is volt inverse, right? So from here we can say that lambda is inversely proportional to L, right? So see, we will write here IDS will be equal to 1 by 2 nu n cox, nu n 1 by 2 nu n cox, here W by L, right? Here VGS minus VT naught whole square. Here we can write 1 plus, okay, lambda VDS, as we have changed the lambda dash by L, this one, okay, by the lambda. This is another process technology parameter with dimension, okay, volt inverse, right? So from here we can see that, okay, we can see that in saturation region, okay, in saturation region our drain current is the function of both the VGS as well as the VDS, okay. So from this expression we can say that our drain current in the saturation region is the function of both the VGS, okay, and the VDS, right? So here if we are okay, making the graph, okay, between the IDS and the VDS as a constant VGS, we have seen that like this, okay. So this is the ID VDS graph where we are seeing, okay, before studying the channel length modulation we have seen that this, okay, this curve is constant like this curve is, let me know here, this curve is constant like this. From here this curve is constant, but because of the channel length modulation, because of the channel, okay, because of channel length modulation, this curve is come, right? Here the, so here the IDS, drain to source current, is increasing. It's increasing in saturation region, but earlier we have seen that the drain to source current is constant in the saturation region, okay. That was the theoretical concept, but practically when we increase the VDS, okay, when we increase the VDS beyond the VD set, the channel and the channel current, or we can say the drain current, is increasing, okay, right? So this is because of the channel length modulation. When we, okay, join all this curve, okay, when we draw all this curve, okay, then it will be cut at a point on a, okay, on a this VDS axis, and that point is called as the early voltage. That point is called as the early voltage, and its value will be equal to the 1 by lambda, right? 1 by lambda. So we can also say that, we can also say here IDS is nothing but 1 by 2 mu n qx W by L, okay, VGS VT naught whole square, right? 1 plus, what is the lambda? Lambda will be equal to 1 upon my VA, then we can say VDS divided, and this VA is nothing but the early voltage, right? So this is the channel length modulation. So what is the channel length modulation? So we can say that when we are increasing the drain to source voltage, when we are increasing the drain to source voltage beyond the VD set, okay, the effective channel length is also changing. Is also the effective channel length is changing, means effective channel length is getting reduced when we increase the voltage drain to source voltage beyond the VD set. So we can say here simply, when we are changing the drain to source voltage, when we are changing the drain to source voltage, right, the effective channel length is also changing, and this is called as the channel length modulation. Okay, this is called as the channel length modulation, right? So we have seen here what is the channel length modulation. For the channel length, so when we increasing the VDS beyond the VT set, okay, our our drain to source current is changing, okay, in the saturation region, and it's basically increasing, right? It's increasing. Earlier it was constant, and this is called the channel length modulation. So let us summarize this. Okay, let us summarize this, and let us see, when we are increasing, okay, when we are increasing the drain to source voltage beyond VD set, okay, VD set, our drain current is now not only the function of the VGS, but it also will be the function VDS, right? The VDS. So when we are increasing the VDS or the VGS, our drain current also increase. Or we are decreasing the VDS and the VGS, our drain current is also decreased, right? So any change in the VGS as well as the VDS, or any change in the VDS or in VGS will change the drain current in the saturation region. Okay, so this was the summary point for this, right? So here we have discussed the current equation, okay, the NMOS, okay, in the NMOS, or we can say N channel. Now we are going to see the current equation for the Pmos. This was channel length modulation. This is important topic, okay. Right, now let's see the current equation in the Pmos. We are saying here current in Pmos. We can also say the N. We can also say P channel mode, Pmos, or P channel, or this channel is containing the whole here P channel mode, or we can say the N type mode, because the substrate is here N. For this mode, we are going to see the current equation. So here, okay, so here the first one is, okay, when the VSG, okay, as I am going to tell you that in the P channel MOSFET or in the PMOS, the operation will be just opposite to the NMOS, right? Just opposite to the NMOS, right? So here in the PMOS, we connect source, okay, to the larger voltage, okay, to the larger voltage, and we connect drain to the smallest voltage, and here we connect body to the larger voltage, that is the VDD or the largest voltage that appear in the circuit or in the IC, right? The source is connected to the larger and the drain body is connected to larger and then is to the lesser voltage, right? In the PMOS, and for the PMOS the VT is okay, negative. VT is negative, right? So please analyze the operation of the P channel MOSFET or the P MOSFET by yourself. If you are feeling any difficulty, please contact me, okay? Through Telegram channel, right? So when the VGS is less than, or we can say when the VGS is greater than VT naught, okay, and the sorry, not VGS, is VSG, okay, it's VSG, okay. So let's see here, when the VSG is less than the VT naught, here I am using the mod of VT naught. For the PMOS, VT naught or threshold voltage is negative. So that's why I have taken the mod here, right? So the VSG is less than the VT naught. Then in this case, this is the case for cutoff. Okay, and here the ISD will be equal to 0. No current is flow through the P channel, right? There is nothing flow, no current flow through the P channel. Okay, and our second, when the VSG is greater than mod of VT naught. Okay, and okay, if the VSD is less than VSG plus VT naught. Okay. Please remember here we are using with sign, VT naught with sign, right? Then our ISD will be equal to, this is the condition for the linear region. This is the condition for the linear or triode region, or we can say the ohmic region, right? So here ISD will be equal to the, okay, nu P, okay, ISD will be equal to the nu P Cox W by L of P, okay, and here VSD plus VT naught, right? Here VSD whole square divided. Here we are going to use the VT, the threshold voltage. So the threshold voltage is negative for the PMOS, so we are using this with the sign, right? So what will be the condition for the saturation region? So our third case is for the saturation region. So if the VSG is greater than mod of VT naught and the VSD greater than equal to VSG plus VT, right? And we are writing the VT naught with its sign. VT naught for the PMOS is negative, right? So here ISD will be equal to, okay, source to drain current, SD will be equal to 1 by 2 nu P, okay, nu Cox W by L, okay, VSG plus VT whole square. Here also we are writing the VT its sign, right? So this is the condition for the saturation. This is the condition for the saturation, right? So this is the current equation for the PMOS or P channel MOSFET or N type MOSFET, right? So when the VSG less than VT naught, here the VT naught is negative for the PMOS, right? So this is the cutoff region, and ISD will be equal to 0 when the VSG is greater than mod of VT naught and the VST is less than VSG, okay, plus VTP. We are writing the VTP or VT naught, okay, with the sign. Okay, we can also say that VTP, right? I am writing here VT naught because I will okay, in the future classes, okay, I will uh, tell you that what happened when the source to body voltage, okay, will be not equal to 0. In this case our VT will be changed and this will be something other than the VT node. That's why I have written here VT node, because I have assumed that the source to body voltage is 0 volt, is at 0 volt, right? So here we are writing the VT node with the sign. Okay, now this is this will be our equation for the current in the linear region or triode region, or we the ohm. Now in the saturation region, this will be the equation of P. So please, during using this formula, okay, please concentrate on the VT node. That here we have to use the VT node with its sign, okay, not only with the magnitude. So in next class we are going to see, okay, how the gate capacitance, okay, how the MOS capacitance we can say vary with the gate voltage, right? So in next class we are going to start with that topic, right? Okay, thank you.